Welcome back to the Packet Lab. Today's lesson is going to be the first in a number of lessons covering frame relay. And today we're going to take a look at some basic concepts of frame relay and just really give you an introduction to the protocol. So as always, we should start out with what exactly is frame relay. Frame relay is a high performance, and I suppose that's in the eyes of the beholder, packet switched WAN protocol. It's going to operate at layer 2, which is the data link layer of the OSI model. Frame relay, as I said, is a layer 2 protocol, and you can use it to transport a variety of routed protocols. So we're going to concentrate exclusively on IP, but do know that you can transport protocols such as IPX, AppleTalk, DECnet, whatever your little heart desires. It doesn't matter, because what's going to happen is that as we progress down the OSI model, we're going to get to layer 3, and that's where your routed protocols exist. It's going to pass that down to layer 2 where frame relay lives. Frame relay is going to slap on frame relay headers, which is going to encapsulate that packet, and so then it's going to use that information to traverse the frame relay network. And a little later on we'll take a look at the concept of the frame relay cloud. So basically what's going to happen is that the frames are going to go out with the frame relay encapsulation, and they're going to go through the frame relay network, and they're going to get switched from frame relay switch to frame relay switch to frame relay switch based on frame relay information, and primarily on something called the data link control identifier. You'll see the abbreviation is DLCI. It's almost exclusively pronounced DELCI, and it's going to use that addressing to get from switch to switch to switch, to go from one side of the WAN cloud to the other. When it hits that far side, it's going to strip off all of the frame relay encapsulation, and then you're going to be left with your layer 3 and above information. So in our case, like I said, IP, it's going to be passed on to the network level to process the IP packet. Frame relay puts data in variable sized units called frames. I'm not going to be very anal about the semantics of using frame versus packet during these lessons. There is a difference. Packets exist at layer 3, frames exist at layer 2. 99% of the time it's not really important to make a distinction between those two terms, because you're just talking about a logical grouping of ones and zeros. There are occasions when you do want to be more exact and specify whether you're talking about frames or packets, and that's generally when you're talking about something that lives in both the layer 2 and layer 3 world. In our case, it's not going to matter for these, so again, just giving you a warning ahead of time. I may say frames when I mean packets, and I may say packets when I mean frames. But I digress. The big bit here is to see that it is a variable size unit, and that differs from a competing WAN protocol called ATM, which is asynchronous transmission mode. No, asynchronous transport mode. I'm not good with the abbreviations. But anyways, I'm not going to go a whole lot into ATM, but ATM uses a fixed, they call them cells, cell size of 53 bytes. So every frame or cell that ATM sends out is a fixed size. It's 53 bytes. Whereas frame relay, depending on the size of the packet that's passed to it, is going to be variable size. So if you give it a small packet, it's just going to send out a small frame. If you give it a big ass packet, big ass frame goes out. So that's important. That's a differentiator from other WAN protocols such as ATM. The other differentiator is that it leaves any necessary error checking, such as the retransmission of data, up to the endpoints. And the endpoints here are going to be basically your routers on either side of the WAN cloud. And it's going to leave this to, in most cases, we're dealing with TCP. Where this comes from is that frame relay came to prominence during a time when another protocol called X.25 was the WAN protocol du jour, and X.25 had a lot of really good error checking. It would do it hop by hop by hop by hop, so it was highly reliable because each hop was doing error checking and making sure that that packet, or frame rather, whatever, again, I'm not going to get into semantics, that logical grouping of ones and zeros was the same that it was when it left point A until it got to point Z in a lot of cases. Frame relay said, you know what? There's other protocols that handle that better, and if we do lose a couple of packets during transmission, not a big deal, because something like TCP is going to handle that for us and just ask for a retransmission. So what this did was it made it a little less reliable in that every packet wasn't checked on every hop, but it sped up transmission quite a bit. That said, there is basic error checking built into frame relay, and that comes in the form of a frame check sequence. And if you're used to the concept of a CRC, then you'll understand what this is. Basically, it's just a quick and dirty algorithm that's run on the frame when it's put onto the wire. It runs the algorithm and it says, okay, my algorithm comes up to 3, the number 3. Pops that value in there. It's going to check it at the next frame switch. It's going to say, okay, run the algorithm again. Okay, it's still 3, keep transmitting. Gets to another frame switch, runs the algorithm again, and it comes up with 4. Well, it's going to say, well, I expected 3, so this is wrong and I dropped this. It's not highly detailed error checking, but it is sufficient for a lot of purposes. If there are changes to the frame, it will catch this. The one thing with frame relay is that it's going to drop that frame. It's going to simply drop it. It's not going to ask for a retransmission. Again, that's what the error checking that's going to be handled by the upper layer protocol such as TCP, that's their job to handle that. So here's a look at the OSI model, and frame relay lives in the data link layer. That also includes the physical, because you have to have a wire or something for it to connect to the network. But the big differentiation here is that here's the network layer, that's where IP lives, IPX, DECnet, and then the transport layer, that's where TCP lives. That's where you're going to have your error handling and retransmission protocols working. So it's a layer 2 protocol. Okay, and we touched a little bit on the history earlier. It arose during the era of X.25. Frame relay first rolled out in 1984, but didn't really take off until the late 80s. And what happened in 1990 was that there was a consortium of the quote-unquote Gang of Four. So it was four of the very large telecom businesses got together to focus on frame relay and to look at developing the technology more. And so the Gang of Four, if you take a look at this, so it's Cisco, which is still around to this day, Digital Equipment Corporation, or DEC, which was eventually bought by Compaq, and Compaq was bought by HP, Northern Telecom, which is technically still around, but I think that they're up to their noses in bankruptcy and probably won't be around long, and then Stratacom, which Cisco bought. Basically, Cisco is the only one of these guys that's still really left, at least the standing of being one of the top 4 telecom companies. Anywho, so what they did was they had this consortium and they looked at creating extensions for frame relay to improve performance and make it the dominant WAN protocol. And what they came up with was a group of extensions that are collectively referred to as Local Management Interface, or LMI, and you're going to hear it referred to as LMI almost exclusively, and we'll look at LMI in more detail a little bit later on in this lesson. And as mentioned earlier, frame relay is an example of a packet switch technology, and there's two aspects to packet switch technologies. The first is a variable length packets, and like I said earlier, ATM uses a fixed packet size, whereas frame relay uses a variable length packet. There's advantages to each approach, but frame relay is going to use variable length packets. And probably more important is that frame relay uses statistical multiplexing, and statistical multiplexing is kind of a strange concept to explain. Let me try it with a really shitty analogy. Imagine that you have two houses, house 1 and house 2. You live in house 1, your neighbor lives in house 2, and you have to get water to those houses. So there's a couple ways you can do that. You can each have a dedicated pipe. So in this case, let's say each house has a dedicated pipe, and each of those pipes can handle up to 64 gallons of water per second. So that's fine. You know, you can get your 64 gallons of water per second. When you look at statistical multiplexing, what it's going to do is say, hey, instead of having two individual fixed capacity pipes, let's have one pipe. So this one pipe is capable of doing, in this case, 128 gallons of water per second. But I'm still going to guarantee house 1 and house 2 that you can have guaranteed up to 64 gallons per second. So nothing really changes there. What the advantage is that let's say you're in house 1 and you want to water your garden and your neighbor's gone to work. So you're going to turn on your faucet and get your 64 gallons per second. Well, when you're looking at that pipe, it's only half full, because you're running at 64 gallons per second and your neighbor's running at 0 because he's gone. So why are we wasting that pipe, you know, that bandwidth? What you can do with statistical multiplexing is you can say, hey, if my neighbor's not using that other part of the pipe, let me use it. Let me get, you know, in this case up to 128 gallons per second, water my garden a whole lot faster, and then I'm done. That's what statistical multiplexing allows you to do, and it does this by putting small amounts of data onto the wire in fixed periods of time, short fixed periods of time. We'll go into this a whole lot more detail, especially when we hit the frame relay traffic shaping lessons, the quality of service lessons. So this begs the question though, if you've got your 128 gallons per second, you're using up the whole pipe, and then your neighbor comes home and says, hey, I want to take a shower, well, what happens then is that he turns on his shower, and remember, he's guaranteed of 64 gallons per second. So let's say that the shower takes 32 gallons per second to run. Turns on his shower, what's going to happen to you is you're going to go down from your 128 gallons per second watering your lawn down to 96 gallons per second, whereas your neighbor's still going to be getting his 32 gallons per second. So you're still getting more than you would with that pipe that would have been fixed at 64 gallons per second, and you're able to use the entire bandwidth of this pipe. Now, of course, if your neighbor says, hey, I need to water my lawn too, and he turns on his sprinkler, that's when you run into the pipe being full, and because both of you are guaranteed the 64 gallons per second, that's what you're going to get. And we'll introduce that with the concept of the committed information rate, or CIR. I hope that helps for understanding what statistical multiplexing, at least the advantages that it gives you.